Assalamualaikum warahmatullahi wabarakatuh. I will start with the chapter 7 about MIPS data transfer and addressing mode. The data storage in programming mainly revolve around the variables and data structures. So variables is something, a simple variable for a single data element, but for to store many elements, we would use a complex structures such as arrays or structures. In MIPS, we have registers versus memory. So the registers is inside the processor that have a very fast access, but a limited number. In this case, for our MIPS, we only have a 32 general purpose register. As for the memory, it can hold billions of data elements. However, they have slower access than registers. But although those two types of memories here has a different limitation, but if combined, it will enable the programs to manage large volumes of data effectively. In the MIPS architecture, arithmetic operations are executed only on the registers. So the MIPS must include data transfer instructions that facilitate data movement between memory and registers. In this case, bila kita run the instruction, the data must be loaded into the registers. So one of the part that you need to learn is that data transfer instructions that move the data from memory to the registers and vice versa. To access a word from memory, a word here means that data in a size of one word. So an instruction must specify the appropriate memory address. Memory can be considered a large one-dimensional array with the address as the index beginning at 0. So we can consider the memory is like a large array, a single dimensional, one dimensional of array. So every single byte in the memory has its own unique address. So this is 1 byte. You can see the arrow here. 1 byte of memory have a different access. Can store only 1 byte, and then to access them, okay, they have their own unique address. Okay, so 1 byte consists of one word. Okay, and then a 32-bit word consists of 8-bit bytes, means that for a cell of 1 byte, so therefore the address of each word is a multiple of 4. So anytime that you want to access to the next line or the next memory address, we can add 4, so to get to the next one word. So in this arrangement, the most significant bit is located on the left, while the least significant bit is on the right. So regardless of different type of processor, okay, most significant bit is always left, and least significant bits is on the right. Okay, and for the sake of simplicity, it means that we in originality they are in a binary, but because of 32 bits is too long, so they use hexadecimal numbers. Okay, so all this data or memory address is in a hexadecimal. You can know it because of the 0x at the front to tell that this is a hexadecimal, right? For example, data. Okay, so the data here is in a hexadecimal also, 0x36A1FDED. So find that data. To find the data, so they must look at the address. So the address is at 1001.004. It's on the second line here. Okay, so you can see 1 byte contain 36 hex, and then the second byte is A1 hex, and then third byte is F2, and then the last one is ED. Okay, and if you look at the memory diagram, so the memory address place the lowest, okay, the lower addresses at the bottom and then go up go at the top if the memory get higher after that. Okay, now it's simply like this figure, okay, the memory layout. So in this case, for our part of data transfer, we play around within the static data and the dynamic data. Okay, so one part that mostly that we use is static data, which start at 0x10000, and then the objects with a size is known at compile time, means that you must configure it during the coding and then assemble it, and then at the time they will be created. So that object or variable's lifetime is available for the entire program execution. For example, the declared variables with an initial value, okay, will be available during the program execution, and after that it will be released after the program has been closed. Then other segment is that we have a stack segment and also dynamic data, which are located on a higher memory addresses. Now, static data is defined as assembly time, means that after you have written the complete code and then there is no error, you click the assemble icon, then if there is nothing problem, they can be created. Okay, the allocation of that for the variable will be placed on the memory, so when the program starts running, so the size, location, and number of variables are fixed for the program's entire execution. For example, a static array of size 10 cannot be resized. So all variables must be declared before the program runs. And where do we declare these variables? You can define it using the .data assembler directive. Then the variables can be allocated on the memory. Okay, the memory range start at 0x100000 and then extends to 0x10040000. So the key characteristic is the same as the previously that I have mentioned, created at program starts and exists until the program termination. And then the data values can be changed during the execution. The size and memory addresses cannot be changed. MIPS architecture support the following data or memory size: byte, half word, word. So byte is an 8-bit integer, half word is 16-bit, and then word is 32-bit integer. We can also have float and double, which is a 32-bit floating point number. When the assembler starts to execute, it keeps track of the next address available in the data segment. Initially, the value of the next available slot in the data segment is set to 10010000. And then, as memory space is allocated in the data segment, this next available address is incremented by the size of the space required. This approach allows the assembler to keep track of where to store the next data item. For example, we have this data assembler that has been declared with N1, N2, and then unidentified label with a dot space. Then N3 is a half word. N4 is also half word. Now let's see what will be the effect with these five uh, data declaration. Now, the data directive will begin at this address 0x1001, okay, and then before the declaration, before the program, after the assembling, and then we don't have any problem before we start the execution. So all these variables has been allocated inside the data segment. As you can see, data segment address start at 1001 here. And then N1 word is AC23, right? So they will be allocated on the address, okay, 10010000, okay, because they consume 4 bytes. So the addresses start from 10010000, okay, at this moment, I would just use only the 4 hex at the back. So start from all 0000 until 0003. So that will be 4 bytes. Then you can see AC23 is inside the slot. After the N2 word 17AA is also 4 byte, so it will start at plus 4, 0004 until 0007. Here you can see 17AA. And then dot space at 8. Dot space 8 means that we have 8 bytes. So 8 byte means we consume 2 words. So it will start at 0008 here because plus 8. And then until 000F. Okay, so this is unlabeled and must be accessed by address. Okay, and next is the half word entry. So entry consists of hex 43 hex, which is only 2 bytes. So it will start at here because the starting index is all 0, and then to go to the cell, so you must plus 10, so you will have 0010. And then because it's only 2 bytes, so it will be until what 0011. So then it will store 0043. See, so the right hex number is 0043 for N3, and then for N4 is also 2 bytes, starting from 0012 until 0013. And they will put the value 0x001f. So now, as you can see, the assembler automatically calculates the next available address after each of the allocation. So using labels like N1, N2 is crucial for organized and maintainable code. Better that we declare a variable so that you can just do the loads instruction or store instruction just using the label. Okay. So for the space here, without this any label, you must calculate. You must have some certain understanding of where the memory will be located, and then you can access it. Okay. Byte order. Okay, so byte order is the convention for assigning addresses to byte within the within the word. Okay, so because we play around, we are operating on a one word, so you need to know the assigning address. So there are two formats: big endian and little endian. If it's a big endian, the leftmost significant bit, the leftmost byte, which is the most significant bit, has the lowest address. But if it's a little endian, the rightmost byte, which is the least significant bit, has the lowest address. Now, in this figure, the left side here is the big endian. And to read it means that to read the lowest address is like you are reading the textbook, the English textbook. You start from the left and then to the right, to the right, to the right. So you can see 0, 1, 2, 3. So this is how big endian is read. And then for the little endian, we start from the right. Like you are reading Quran, Jawi. So you read from the right. 0, 1, 2, 3. And then repeat back again to the right side. 4, 5, 6, 7, 8, 9, A, B, something like that. Okay. Now, the processor can operate using either byte order. Okay, so the most significant bit is always on the left, least significant bit is always on the right. Okay, and the address of the 32-bit word is the same in both formats. So don't get confused. Okay, if your other friends or the other laptops, okay, shows a different output, it's because of the byte order. Okay, so the difference is that the individual byte addresses. If it's using a big endian, okay, the reading or the address would be from the left side to the right side. And then for the little endian would be different format. Okay. So for example, given a word 1A, 2B, 3C, 4D. Okay. For big endian format, they would be placed, okay, from the left side. Okay, left side is the lowest one. The lowest one here. If we start from the left side, 1A, 2B, 3C, 4D, big endian. But for least significant, for little endian, we start from the least significant bit from the right side. 1A, 2B, 3C, 4D. You will be able to see that inside the Mars. Okay, and you can determine if your processor or your computer is a big endian format or little endian format. Okay, now big endian, in a real world example, mostly used by the IBM Power PC, previously used in the Macintosh computers. Little endian used by Intel and ARM. Sometimes ARM or versions can also support big endian. Okay, now we have introduced the layout of the memory. Now, how do we want to access this memory? Because you need to know if yours is a big endian or little endian. Now, then the next part is that how do we access it? All access to memory performed by using some variant, because we do have several types of instructions. Okay, so it's under the load or store instruction. So these instructions include loading or storing a byte, half word, or word. So there are three variants: load word, store word, load half, store half, and then load byte, store byte. So if we transfer from memory to register. Okay, I'll use an arrow to show you. So from memory to register, like this. So the action of transferring a word from memory into a register is known as a load operation. Okay, because from memory to register means that you want to transfer from the memory to register to operate. So you load them. Okay, next is register to memory. It's like once you have processed the data and then you want to store back to the memory, then transfer from register to memory is using not load, store operation. Okay, so it's a store operation. Okay, so store operation can be store byte, store half, and store word. Okay, load and store instructions is under the I format. Okay, the syntax is in the table here. Let's say you are using load word. So you will need a register, okay, RT, and then immediate of where how many bytes do you want to jump, okay, to go to. Okay, and then RS is the load the base address of the memory that you want to go. Okay, so usually the bracket here shows this is a base address. Now this one RS here is the base address. Contain base address. It must be a legit base address. Okay, in this case, using your data segment, the real data segment, it should contain 0x10010000. Okay, so for example, we have load word T320A0. Here, it should contain the base address. Now, the base address is 1001. For example, this is like 10010000. Now, this base address will be added with plus 20. Okay, 20 here is a not hexadecimal. This is a decimal. Okay, so you need to convert it into hexadecimal number first, then you can add it together with this memory address. Okay, so this is the syntax. Here it means, okay, this network, okay, we find the address and then find the content inside of it and load it inside the T3. Okay, so now the T3 will contain the data from this calculated address. Here you see the operation is that memory. Okay, they find the memory address from the immediate plus RS content. and you will get the memory address, and then they retrieve the memory content and then put it inside the RT. Okay, the same thing happened for the store word, but this time you want to store the data from the RT, okay, to the memory register, memory address that has been calculated. Here, the memory address that we calculate is that immediate plus, okay, the base address, which is sometimes 100100, that's the default one. So we plus that one. Okay, once we have calculated the address, okay, then we can transfer, okay, the content inside, okay, inside this register, okay, so to this memory address. Okay, now for example, store word S012T3 here means that they calculate first the memory address 12 plus address in register T3 plus immediate 12, okay, then the content inside S0 will be saved, okay, will be saved into this memory address. Okay, now the effective address of the desired memory word is calculated by adding an immediate, here IMM is immediate value, to the contents of the RS register. So the content of the RS register is referred to as base address. Okay, usually we call it as a base address. So the number outside of the bracket here, we call it as offset or the immediate value. Okay, in the I type, we call it as the immediate value. But in this case, for the load operation or store operation, we call it as an offset. Offset here means how many bytes do you want to jump from the original or from the starting point. So this offset will adjust the target address by a specific amount, either positive or negative, relative to the base address stored in the RS register. Okay, so for example, load word T0 for A0. So the program or the CPU, the processor would load, okay, word or data from address in A0 plus 4. So you should put A0 plus 4, okay, and then load it inside the T0. And then we do some simple operation ADDI T0 T05. After that, store back the content inside T0 into the next word, okay, because this one is 8, so means that into the next word A0 plus 8, okay. So this is how the operations is done. In line to the load instruction takes the base address stored in register A0. So A0 here is on RS. It's always, the base address is always on RS. And then 4 is the immediate. And then T0 is the RT. Okay, now they want to calculate the target address. Okay, the effective address. So the content inside A0, this one, okay, because RS is A0. Now the content inside A0 is 1001,004. Now they will load into the ALU, and then they take out the immediate, which is 4. Okay, so 4 plus 004 is 008. So the effective address is 008 here. Now, because this is a load word, means we need to load the whole word here. So the load address, the data that will be loaded, okay, because this is using a big endian. Big endian means the smallest one is the left side, the most significant bit, B5. So B5, okay, and then they arrange 76, and then 89, and then 50, like that, okay. But if it's a little endian memory layout, it will be loaded like this. It will be in the inside of the memory will be like this: 50, 89, 76, B5, like that. Okay. Now, as for store word, okay, store word, same thing. A0 is the RS, 8 is the immediate, and then T0 is 8 in a register number. So when they load the A0 is still 004, add with 8. So 4 plus 8 is C in hexadecimal number. Now this will be loaded here 508976 PA. Right? Now that's how we load the load word and store word instruction. Okay, example, given the memory content and addresses in the figure, write an instruction that load the byte at address 0010 into register S0 using the base address found in register T1, which contain the base starting, of the data segment lah. So all zero lah, 0000. Okay, now how do we do that? The solution is that because we want to load a byte, okay, so you just want to load a byte, okay, which need to reach the effective address 0x10. Okay, now we can use the command load byte, okay, and then into register S0. So we want to load into register S0, and then from the base address is from T1. So we use a bracket T1. Okay, the only immediate that we need to know is that, okay, we want to load from the byte address, this one. So subtract. Okay, subtract to this number. Okay, 0010 subtract to 000, you will get 0010. So don't forget to put a 0x at the front. Now this is your immediate. Okay, now once you get the immediate, then you can put it on the immediate here, 0x10. You can also because we are using a hexadecimal, yes, you can put a 0x. Okay, and then if you want to represent it using a decimal, yes, you can convert it using a decimal. Okay, now once this load byte has been operated, so 16 or 0x10 plus 10010000, so you can find 0010 here. And then because this is only one byte, load byte, so means only one byte will be taken out. So see the arrow here, only C1 will be loaded inside the S0. Okay,